So this looks a lot like what my classes look like. We do a lot of like, here's a little intro to something, now work on an activity. Me and a couple of peer mentor students walk around and answer questions, and then we stop and look at something else. So I hope that was helpful for all of you guys. I also like the fact that everyone was kind of helping everyone else, so I'm relying on the peers amongst you to kind of help and figure things out. It's very much a group activity. What we're going to do now is to migrate to an entanglement source. And I'll show a picture of what this looks like. Let's see. Well, I don't know. Okay. This is an entanglement source. So entanglement source, it's this funny looking little thing. And we're going to just set it with all the default values. And we're going to operate it kind of similar to how we had with the coherent source. It's going to be a little bit different because it's got two outputs to it. And then I guess one of the configurations you can use on it, you can define whether or not the outputs go like left and right or left and down. And so I've got this set up so that it's going right and down. So one of the outputs is going into the interferometer, and then another output is going to a third detector over here, which I don't think you can actually see my cursor here, over here. And there's a polarizer here, kind of like the polarizer we had before. This polarizer, again, can be set to 0 or 45. And what we're doing now is this is an entanglement source that is set up as, it's called type 1, which means that the polarizations are positively correlated, so you should get like HH and VV and so forth. And what we're doing now is detecting on this third detector as a kind of herald, where we're going to say, okay, once we've detected on that side, that like heralds the existence of the photon on the other side. But because we've got this polarizer here, it's only going to click when it detects certain kinds of polarization. And in particular, if we set this to 0, then it's going to be clicking on 45 degrees. If it's set to 0, it's going to be clicking on horizontally polarized. If it's set to 45, it'll be looking for diagonally polarized. So this acts kind of like what we had before, where you are conditioning on the polarization being diagonal over here, and that means that the light on the other side will also be diagonal, and then it acts like an eraser. But if you set it to, say, 0, then it's triggering on horizontally polarized, and what you see looks like horizontally polarized. So you should see the exact same effects, but this is more of the traditional quantum eraser, and this is the experiment that Tori is going to show you, where you're going to use an actual entanglement source and use this third detector as a trigger for what happens downstream. The sort of magic of the quantum eraser is that it is affecting, and again, we use that causality word improperly. It looks like it's affecting what's happening in the interferometer remotely on this other detector. One thing that I do want to caution you about is that path lengths are very important here because we're doing coincidence counts. That's why I've got this kind of bendy path for the other one. You want to make sure that the number of steps to each detector is the same. I think in this one it's 11 steps. Otherwise, the whole thing's blown out of the water. So I want you to try this with the setup you have already. Just take out the laser and then do the same thing. We're going to set the polarizer to either 0 or 45 and then set the angle for the halfway plate to get that particle or or wave-like behavior. Okay. Anyone have any questions about the setup? I'm going to be walking around for the next 15 minutes, next 12 minutes. It's an entanglement source. Mm-hmm. Okay. I'll let you guys have that. Okay, glad to see everyone's having fun. I guess we have a break after this, so formally our lesson's over, but of course you're free to continue playing around. Hopefully what you saw from this was a recreation of what you saw on the classical side, where if you herald on horizontal, with this being 0, and the halfway plate is 0, then it looks like you're heralding on horizontally polarized light. What enters in is horizontally polarized, and you should see dominantly D1 triggered by D3, and less so this. And then if you turn it to particle-like behavior by changing the halfway plate to 45 degrees, then you should see these two being equal, roughly, right? And then when you switch this back to 45 degrees, then you should recover that wave-like behavior. D1, D3 is dominant. Okay. So I hope this was helpful. We are going to look at the real version of this, so you can see whether or not this was helpful to learn this way, and then this way, some of the differences between simulation and the real world. I think this will be kind of an interesting thing to do. And then I'll be around during the break if you have any questions.
Is this table here?
What's that?
We're going to be testing on the table, right?
It's in Justin's little fortress of solitude over there. I was just dismissing class. So I guess we have a minute or two if you want to ask questions, but you can just catch me during the break. All right,
Yeah.
cool.
Thank you, Brian.